Okay, so we've been talking about dilution here and solution stoichiometry, which is where we're going to get into. And as I mentioned, next week we're doing titrations, which is basically solution stoichiometry. And so this hopefully should be relatable. So we finished up last time there talking about the dilution equation. And again, a reminder, as we mentioned at the end, you can in the M1 V1 equals M2 V2 leave the volumes in milliliters. Or you can convert it to liters. It will work out either way. Obviously, if you leave the volume in milliliters, in this case, when you solve for volume, it will be milliliters. And if you leave it in liters, when you solve for volume, it will be in liters. So you just want to make sure you keep those two things sort of right in your head so you don't get the wrong sort of calculation or anything like that. Also, as I mentioned, you can use this in more of the C1 V1 equals C2 V2 using any type of concentration unit for a solution in there. So why don't we try one here? So why don't you do this one? How would you prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock solution that is 4 molar? So take a couple of minutes and see what you come. Okay, let's take a look at this one. So this is definitely a dilution. We're starting with nitric acid. We are ending with nitric acid. They're both the same. We basically have a bottle of nitric acid that's sitting there that is 4 molar. We want to make a new container there that has a volume of 60 milliliters and a molarity of 0.2 molar of the nitric acid. So this is definitely a dilution type of situation. We have M1 V1 equals M2 V2. In this case, really the more dilute guy is usually the N2s, but it really doesn't matter as long as you keep everybody together that goes together. So V2 would be 60 milliliters. M1 here would be 4 molar, and that means that we are going to be looking for V1. So again, in this case, I can leave it in milliliters, and if I solve for V1, that would equal M2 V2 divided by M1, dividing this to the other side. And putting numbers there, we end up with 0.2 molar, our volume being 60 milliliters, and our original molarity of 4 molar. Again, here it works out okay because the molarity on top and the molarity on the bottom cancel out. That leaves us units of milliliters. And if we do that, 0.2 times 60 divided by 4 gets us 3 milliliters. First off, any question? 3 milliliters is 3 milliliters of nitric acid. It's really 3 milliliters. And in most cases, when you solve for V1, it is 3 milliliters of the more concentrated thing. So you're going to take 3 milliliters of your more concentrated solution and dump it in there. Should I dump 60 milliliters of water in there with it? The answer is I should not, because if I dump 60 milliliters of water in there with it, my total volume would be 63 milliliters, right? And we want a total volume of 60 milliliters. So a very common question that you're asked on a dilution problem is not necessarily maybe how much of something that you need, but a lot of times you're asked how much water that you need. And in most calculations, the amount of water is V2 minus V1, basically, is how you get that. So in this case, our final volume is 60 milliliters, and we already put in there 3 milliliters. So we need about 57 milliliters of water to be added to that. So we would add our 57 milliliters of water along with our 3 milliliters that we put in there, the more concentrated guy. We would have a total volume of 60 milliliters. When we give it a mix and shake here, we will with a solution that has a 0.2 molar. So why don't you try another one? Here. how much water is needed to make a 155 milliliter of 0.650 molar sodium chloride solution from an 18 molar sodium chloride solution. All right, so give that a go, see what you come up with there. Same situation here. We basically want to make a more dilute solution of sodium chloride. We have a more concentrated solution. So once again, we have a bottle basically of 18 molar sitting there on the shelf. And we want to make a new container again that has a volume here of 155 and a molarity of 0.65 molar. So once again, we're going to do an M1V1 equals M2V2. In this case, we do have M2 and V2, which is our more dilute guys. We also have the molarity there of our more concentrated guy, which is our 18 molar. So we're going to solve for V1 again, and that's going to be M2V2 over M1. And I am going to leave it in milliliters in this case because it's okay to do so. And again, here our molarities will cancel each other out. That leaves us milliliters as our unit that's left over. And in my made up number here, we end up with, we'll call it 5.60 milliliters. Again, that is 5.60 milliliters of our sodium chloride. That is essentially what we're going to take from the more concentrated bottle into our new bottle that's empty. So we'll put in there 5.6 milliliters of the more concentrated guy. We are interested though, again, and we want to be careful on these type of problems because that is the question that is usually asked or a lot of times asked, which is how much water. So we do want to figure out the volume of water by really taking our final volume and our initial volume, taking the difference. And in this case, our final volume is 155 milliliters. We already put in there 5.6 milliliters of our sodium chloride solution. So 155 minus 5.6 means that we do need to put in there about 149.4 milliliters of water. So once again, 149.4 milliliters of water. That will give us our total volume of 155 and also the correct concentration when that is all mixed together in this case. Any questions on dilutions? So again, dilutions are pretty straightforward, not too bad. A lot of times people do miss the question about how much water and they just do the M1V1 equals M2V2 calculation and give that as the answer. So make sure you do read it carefully. And as we mentioned earlier, make sure that you do not use the dilution equation here in places where you should not use it, namely really solution stoichiometry type problems. Any questions on that? So we're going to talk about next really solution stoichiometry type of problems. And really the good news about sort of solution stoichiometry problems is it really is the same sort of steps that we've done in basic stoichiometry problems. The only difference is we are using solutions, which means in most cases we will have molarity and volume sort of involved. And that means that we really can follow those same 4 steps. So when we look at a solution stoichiometry sort of problem here, we really do follow those same 4 steps of you always want to make sure it's a balanced equation. You want to convert to moles. You want to do the mole to mole relationship. And you want to convert moles to some other unit. Now, in this solution stoichiometry problem, you can absolutely have a limiting reagent problem that occurs. I would say probably in a lot of cases, it's going to be a more basic stoichiometry problem, but definitely you could still have a limiting reagent type situation that occurs. That means in addition here, you may have to do the limiting reagent step, obviously. And that means that you can either obviously do the step like we talked about before, that calculation between reactants, or you could do an ice table in that case. If it is a basic stoichiometry problem, I would probably recommend just doing it as a stoichiometry problem, not an ice table. Again, I would probably save the ice table approach for just limiting reagent type situations. That's really kind of where it's the best at, I would say. And for basic stoichiometry problems, you should just do the stoichiometry calculation. Now, what is really the main difference? The main difference is because it deals with solutions, we have molarity involved, and more particularly, we use the molarity equation to do a couple of different things. Very common in solution stoichiometry problems, the second step, where you would convert to moles. You would use something like the moles is liters times molarity. So instead of using grams of molar mass from the periodic table to get the moles, you could use the molarity and the volume to get the moles, and that's a very common place where it sort of differs. Everything else after that's pretty much the same. The second place where kind of it could be different is at the end here. So in a lot of examples up until this point, we had moles and we took moles to grams using the molar mass. Common in solution stoichiometry problems is you could use the moles and the molarity to get the volume using the molarity. You also could use the mole to calculate the molarity. So that's sort of a variation on the last step of the stoichiometry process. A lot of times you're asked for volumes of a solution. You're also sometimes asked to figure out the concentration or molarity of a solution. And sometimes you may be asked just to figure out grams as well, like normal. So somewhere along the way, either in step number 2 of the stoichiometry process or step number 4 of the stoichiometry process, somewhere along that way, molarity gets involved, basically. So molarity and volume gets involved. Everything else is the same, balance equation, mole to mole relationship, all that's the same. But again, that sort of insertion of molarity at those 2 spots in the process is really what it happens. And again, you can still do obviously a limiting reagent problem. If you are given a limiting reagent problem that involves solutions, you will still know it's a limiting reagent problem because you can still get to moles. So again, if you have molarity and volume of each reactant, you definitely will know that it is a solution stoichiometry problem and a limiting reagent problem because you could get the moles. Any questions on that there? So, for example, let's take a look at one type of place where, say, solution stoichiometry can't come into play. Let's say we dissolved an unknown substance in water and we did a little gravimetric analysis. And this is kind of similar to some of the stuff that you've done earlier. But a lot of times we could do something like a precipitation reaction. And we may be interested in the amount of precipitate that we actually made. And to do that, we would make the precipitation reaction in a solution, obviously mixing a couple of solutions together. We get this solid, we would filter it. And what we would end up with on our filter paper is the solid at the end, the precipitate. And we can let it dry, which you would want to do as we talked about with percent error. If you don't let it dry at that point, you'll have a very high percent error because you have a lot of water weight that's not actually your product being made. So this is one very common place where you can do something like solution stoichiometry. So for example, if we took this thing and we took, let's say we did, we want to know how many grams of lead to iodide we would produce if we mixed 25 milliliters of 0.25 molar lead 2 nitrate with, we'll go with 35 milliliters of potassium iodide. And this reaction looks something like this. You should recognize this as a double displacement reaction, right? So we get some KNO3 and we get some PbI2. All right, so I'm gonna let you try it now to see what you come up with. Give it a step, follow the same stoichiometry steps. Again, the difference here may just be molarity and volume. I'm gonna give you some numbers here that probably would be helpful. So lead is 207.1, lead 207.2, nitrogen 1401, iodide 126.9. So I think that might be all you need, actually. Might not even need all of that. And I probably should give you a molarity here on the second guy. So let's go with 0.55 molar on that guy. Okay, let's take a look, see how you're doing, and just make sure everybody's on the same page in terms of the process here. So this is definitely a stoichiometry problem, as we have an equation and we got obviously some stuff given to us. So we do have 25 milliliters of this guy, and he has a molarity of 0.25 molar. We also have 35 milliliters of this guy, and his molarity is 0.55 molar. So the first thing we want to think about is this a basic stoichiometry problem, or is it a limiting reagent problem? Is it a basic or limiting reagent problem here? This is a limiting reagent problem, and that is because I have the molarity as moles per liter. I have the molarity and the volume of each of those, which means I could get to moles of this guy and I could get to moles of that guy. And that is basically the definition of you need to figure out the limiting reagent in this case, right? Now, if this problem was different and we were only given, say, the lead 2 nitrate and nothing else, then it's a basic stoichiometry problem. So again, those are things you want to look for. You can still get a limiting reagent problem and a solution sort of stoichiometry problem. So the first couple of steps are really the same. We want to make sure that the equation is balanced, which in this case it is not. So we do need to balance it. And I think we need to lay up a 2 there and a 2 there. We'll balance it again, just using the polyatomic ions as our guide. We had 2 nitrates on the left, 1 on the right. So put a 2 in front of the KNO2, gives us 2 of the potassiums, also gives us 2 iodides, and we got the 1 lead. At this point, the second part of this calculation is really the same, except that instead of using grams and molar mass to get the moles, we're going to use the volume and the molarity to get the moles. So to get the moles of our lead 2 nitrate, remember that we do need to convert our milliliters into liters. So you're going to divide by 1,000 or move the decimal place, and that will get you 0.025 liters. I am going to use my molarity with both units there in a conversion factor sort of way. So that means that I'm going to take 0.25 moles per liter of my lead 2 nitrate. That's going to give me moles of 0.025 times 0.25, 0.00625 moles of my lead 2 nitrate. I'm going to also do the same thing for my other reactant, which is my Ki. I'm going to take my volume and convert it to liters. I'm also going to turn this into 0.550 moles per liter and use it as a conversion factor so I can see both units. When you divide the 35 by 1,000, you end up with 0.035 liters. Once again, using the molarity as a conversion factor, 0.550 moles per liter. And that gets us 0.035 times 0.55, 0.01925 moles of Ki. First off, any questions on those steps so far? So since I'm running out of room here on this page, what I'm going to do is actually I'm going to do the other version. I'm not going to do an ice table here. You can do an ice table if you want to, but I'm going to do the other calculation that we talked about, where I'm going to figure out which one's the limiting reagent. So to figure out how much of the lead to nitrate is needed to use up all of the Ki, I'm going to take my starting moles of Ki, and I'm going to write it correctly, hopefully. I'm going to try that again. Point 0.01925 moles of Ki. It is from the equation a 1 to 2 relationship between those two guys. So that's going to give me 2 moles of Ki and 1 mole of my lead to nitrate here. And that's going to tell me that I need 0.009625 moles of lead to nitrate is needed. So remember, in this approach, you take how much you need and you compare it to how much you are starting with. And in this case, do I have enough? And the answer is I do not have enough, I don't think, right? I need 0.009 and I'm starting with 0.006. So I compare, do not have enough. And because I do not have enough, that means that this guy right here should be my limiting reagent. Any questions on that there? Because that is my limiting reagent, I'm going to use the limiting reagent to figure out how much product I'm going to produce. And if I do that, I will go with 0.00625 moles of my lead to nitrate. I'm now going to do the mole to mole relationship between my lead to nitrate and my product, which looks like it is a 1-to-1 relationship. So that's not too bad. 1 mole of my lead to nitrate gives me 1 mole of my lead to iodide. Those are going to cancel. You could get an answer at this point, which is obviously the same number in this case because it's a 1-to-1. Or you could continue on and use the molar mass of lead to nitrate, lead to iodide, which would be this guy and that guy doubled. So that's going to be 207.2 plus 2 times 126.9. Going to give me 461 grams of PbI2 per mole. Moles will cancel. And we will end up with about a whopping 2.88 grams of this solid would be produced in this case. This is your theoretical yield. And hopefully you could see that it is really the same 4 steps that we talked about previously. We want to balance the equation, convert to moles, which was the only different part that we've done before. It is the mole to mole relationship once we figured out the limiting reagent here, and convert those moles to something else. So it is the same 4 steps. We did need to do the additional step of the limiting reagent in this case, and you could have done an ice table as well. It should come out the exact same way if you chose to do the ice table in this case. Any questions on any of that there? So in this case, we actually did use molar mass at the end, but again, very commonly you sometimes will use molarity at the end of the calculation too. Any questions? All right, so that's a very common calculation for this type of preparation, gravimetrical analysis, where you really do sort of achieve a solid at the end. The next thing that we're going to talk about is titrations. And titrations is another very common solution stoichiometry sort of situation. And when we do titrations, we usually do it by using a solution of known concentration. So there's sort of like a known solution, like the molarity of it, for example, how much of it did you use? And there's oftentimes a solution that's like an unknown solution, like that's what you're trying to find. And to do a titration, we use a burette, which is this long glass tube that you will use next week. And we add from the burette to another solution. And we continue to add basically from one to the next, from the burette, for example, to the beaker, the flask, whatever it may be, until it reaches what is referred to as the equivalence point. And the equivalence point in a titration, and especially like the ones that we will be doing, which are acid-base titrations, is the point where exactly the moles of the acid will equal the moles of the base. So the equivalence point is pretty much where the neutralization sort of occurs in a acid-base titration. So if you remember when we talked about acid-base reactions, it's sometimes referred to as a neutralization reaction. And when you reach the equivalence point in a titration, that is the exact point where the moles of the acid equals the moles of the base. There's also another terminology that's sometimes used in titrations, which is the end point of a titration. The end point of a titration is pretty much where you lay up your titration and call it a day. And hopefully, if you did a good titration, your end point and your equivalence point should be pretty much the same spot, because that is usually when you do a titration, especially in this class. When you go to the next class, you go past it, but usually you want to stop at the equivalence point. How do we know when we should stop at the equivalence point? We usually will use an indicator when we do a titration. So the indicator is usually added to the flask or the beaker. And indicators are usually work over a pH range. So for example, phenolphthalein, which is an indicator very commonly used, and we'll use it next week as well, is an indicator that works over a specific pH range of something like 8.3 to 10. Now, when we look at the pH, anything below 7 is acidic, anything above 7 is acidic, and at 7 is neutral. So really, phenolphthalein works in the basic range of the pH scale. And at 8.3, our good friend phenolphthalein is actually colorless. As you kind of move up the pH scale, becoming basic, it becomes more and more pink in color, like we could kind of see over here, kind of pink in color. And that means that phenolphthalein is colorless in acidic solutions. It's actually colorless in neutral solutions, but it does turn this pink color in basic solutions. And the type of titrations that we will be doing, it's a good indicator because your equivalence point is in the basic range. So when you choose an indicator, you always want to choose an indicator that will actually change color around your equivalence point. So you can actually visually see, oh, it changed color. I should probably stop my titration at that point. For example, if we were doing a titration where the equivalence point was acidic, phenolphthalein would be a terrible choice as an indicator because it will just be colorless all the way through until it becomes basic. And at that point, when it becomes basic, you're way past the equivalence point and you did not stop at the correct time. So there are different acid-base indicators that are used, and you always want to choose one that you can visually see that color change near the equivalence point. Usually when you use something like phenolphthalein, you do those type of titrations, you want to stop the titration when you see the first lightest, super lightest, I gotta hold the thing up to some white piece of paper or the whiteboard here to actually see the pink color. Like if you take it away, I can't even really see the pink. That is technically where you really want to stop in a titration. And that is because your equivalence point in most of the titrations that you use phenolphthalein for are in that neighborhood right there in terms of pH. which is actually the colorless part of the indicator. But if you could get it to just where it starts to turn that super light pink, you know you're probably near the equivalence point, and you can stop and know that you probably stopped at the right point. The other thing that you will commonly hear when people do titrations, and I'm sure we will hear it a lot next week, is I only added 1 drop and the thing went from like no color to super dark pink. And that is a very common thing that occurs when you're doing a titration. So as you're doing this titration, for example, if we have some sodium hydroxide up here in the burette, which is a base, and down here you have an acid, as you drop that sodium hydroxide or that base into the beaker, you will see the pink come because there's a lot of base really quickly till it gets diluted. And the pink will come and go away. And then you'll add more, the pink will come and go away. And you'll continue to add that, and you'll see as you approach the equivalence point, you actually will see the pink kind of stay longer before it goes away and longer before it goes away. And that's a pretty good indication that you are coming near the equivalence point. And you usually want to kind of slow up at that point when you do it. And ways that you can slow up, we could kind of talk about next week. But you could take the burette, for example, open it up and close it, let like a little drop kind of form, wash it down with some water to dilute it, and add what is sometimes referred to as a half a drop. So you're not adding like a full strength drop of base in there that would make it change. Now, why does it do that? Why does it like change colors super quick when you just added 1 drop? And it really throws people for a loop. You'll learn more about it in 200B, but just to give you a quick answer, if you were to graph what is sometimes referred to as a titration curve, and this is like volume of base that's added versus pH, what you will see in a titration like you do is a curve that will look something like this, where the equivalence point would be perhaps here, for example. And what that means is as you approach the equivalence point in this titration, you are going pretty vertical at this point, right? So you're going pretty vertical as you get to the equivalence point. And typically speaking, you actually will see a big jump in pH to the equivalence point, and then you'll actually see a big jump in pH after you pass the equivalence point. And that's why you get this kind of vertical rise as you approach the equivalence point. What that means when you're physically doing the titration is, if I am approaching the equivalence point, my pH up here is quite large, my pH down here is quite small, and my pH here is at the equivalence point. Although those are 3 different pHs, right? Is there a big difference in the volume of all 3 of those? Because it goes vertical, the volume pretty much is the same for all of them. And that is why when you do a titration and you just add 1 drop going, hey, it's just 1 drop, it's not going to make a big difference. When you get close to the equivalence point, you do not need a lot of volume to change the pH a lot. But what it does to your indicator that's in there is, because you change the pH a lot, you go from like no color in your indicator to now you're closer to like the pH of 10 on your indicator, which the pH of 10 on your indicator is now like super dark pink. My favorite color, by the way, when you do a titration, super dark pink. And that's why you'll see that really dark pink that will happen. So you will hear people say that next week. It just naturally comes out. I just added 1 drop. I don't understand. So that's when you start to see that pink color stay longer and longer. You do want to kind of slow it up. You do want to do things like half a drops where you kind of dilute it down, but you will get that really big jump in pH. So I'll give you the truthful chemistry answer, which is, does the color matter? You should be conscious of the color as you're doing the titration. Should it be like, if you get a dark pink color, should you redo the titration? The answer is probably not. A lot of chemistry teachers will tell you, oh, that's way too dark, go do it again. I know people will do that. But what's really important is, if you are careful and you don't titrate like me, where you just open it up and let it all flow in there and then shut it and go, cool, pink, I'm done, right? If you're kind of careful as you're doing it, and you're really careful as you're doing the titration, it's more important that the volume that you get to the equivalence point is about the same in every titration, regardless of the color. The color is not all that important. Why people say the color is really important and you got to get that super light pink and not the dark pink is, if you were to titrate like me when I was in school, because, you know, I wanted to go home, right? So I did 3 titrations in 5 minutes and I was done, right? They're all pink, I'm good. But I could get a dark color of pink over here at a pH of 10, right? or whatever it may be, which is really not too far off in terms of the volume of your equivalence point. But if I was not careful and I shot way over here, I am still going to get that really dark pink, right? The same dark pink that you got over there at this spot. But am I close to my equivalence point at this point? I am way past it. So that is why people and teachers will tell you should try to get the light pink. And if you don't, you should do it again, because they want to avoid you just opening it up, shutting it, and being way away. But if you're really doing the titration correctly and are careful, I wouldn't be super concerned about the color. Really just the volume of each equivalence point that you get, or where you stop, is really more important. Any questions on that there? Okay. So ideally, that's not a bad color of pink. Even lighter is, much better sometimes. But again, you should be concerned about the color, but don't be super hung up on the color. Again, it's more important. That's the kind of consistency and the volume that you add in terms of the base, for example, to reach the equivalence point is actually more important. All right, so titrations, though, do basically result in solution stoichiometry problems occurring. So, for example, why don't you give this one a go? What volume of 1.42 molar sodium hydroxide is required to titrate 25 milliliters of 4.5 molar sulfuric acid? So the titration here setup is we have the sodium hydroxide up in the burette, and we have the sulfuric acid down here. We're adding the base to the acid. This is a solution stoichiometry problem. So follow the 4 steps like we were just talking about. Decide if you need to do limiting reagent or not, and go forth and see what you come up with. And then we will talk about it here in a second. Okay, let's take a look at this one here and see what's going on. So in this case, it's a titration problem. So pretty much a titration problem is definitely a solution stoichiometry problem. They'll sometimes say titration in there. They might even say like how much to neutralize or something like that. But definitely if you got like an acid and base sort of in the problem, it's going to be basically an acid-base neutralization sort of reaction, and it's going to be stoichiometry. So because it is stoichiometry, we always need to have the equation. So we want to do our equation here. So we have our sulfuric acid, H2SO4, and we have our sodium hydroxide. Once again, as we talked about last time in terms of acid-base reactions, they do fall under the double displacement reactions, and that's basically what is happening here. You also should know that when you have an acid and base, you should create a salt and water, basically. And that's what happens when the H and the OH come together and our sodium and sulfate come together. Remember that you do want the correct formulas here. So that's going to be an Na2SO4 as sulfate is -2 and sodium is +1. And we will then make water from our acid and base coming together. Now that we have the proper formulas down, we do want to balance the equation because it is not balanced here. And I believe we will need a 2 in a couple of spots, maybe a 2 there, and probably like a 2 there, I think. That's going to give me 4 hydrogens on each side, a couple of oxygens plus 4 more, 6 on each side, a couple of sodium. So we should be balanced at this point. And obviously 1 sulfur on each side. Any questions on the equation there? And again, this would be our salt, and that would be our water that we make when we have an acid and base to react, as this is an acid, obviously, and that is a base in that case. Now that we have it, we really want to identify what type of stoichiometry problem is this. Is this a basic stoichiometry problem? Is this a limiting reagent type problem? So we could just pull out the information from the problem. We are given that this guy here is 1.420 molar, and we're looking for a volume here. We also know that we have 25 milliliters of this guy, and it has a molarity of 4.5 molar. Is this a limiting reagent problem? The answer is no. First off, we're not really even finding anything on the product side. But secondly, the only one that we could get to moles of is actually the sulfuric acid. We don't have a way to get to moles of this guy, right off the bat. So we don't have the moles of each of our reactants. So this is just really a basic stoichiometry problem, which means we're just going to follow those 4 steps, which is balance the equation, convert to moles, and so forth. Now we are looking for the volume of our sodium hydroxide, and we do have the molarity given to us, which is moles per liter. So we do have the molarity. We are looking for the volume. That means really the thing that we're missing in order to solve this problem is the moles of the sodium hydroxide. And that's really where the stoichiometry is going to come into play. We're going to use the stoichiometry to allow us to figure out how many moles of the sodium hydroxide we would need. Any questions on that there? All right, so clearly the place where we need to begin is with the moles of this guy, because that's the only thing that we have. We do again need to convert our volume into liters, so we could divide by 1,000 or move the decimal place. Either way, that gets you 0.025 liters. We're going to use our molarity here as 4.50 moles per liter, so we can see both units. So that would be 4.50 moles per liter of our sulfuric acid. At this point, the liters will cancel, and we will end up with moles, which is 0.025 times 4.5 gives us 0.1125 moles of our sulfuric acid. So we basically have now just done step number 1. We've done step number 2. We don't need to do the limiting reagent step because it's not a limiting reagent problem. So the next thing that we would do is do our mole to mole relationship, because we need to figure out the moles of our sodium hydroxide. So from the equation, we could see for every 1 mole of sulfuric acid, you get 2 moles of sodium hydroxide. So that's going to be our mole to mole relationship that we will use. We want to cancel out the sulfuric acid. So 1 mole of sulfuric acid on the bottom, 2 moles of sodium hydroxide up on top. The moles of sulfuric acid will cancel. Timesing that by 2 gets us 0.225 moles of sodium hydroxide. That is basically step 3 of our stoichiometry sort of procedure. Any questions on that? Now, in this particular case, step number 4, we are not going to use molar mass because we're not interested in grams, but we are interested in volume. Now that we have the moles of sodium hydroxide, we can use the molarity equation here to figure out the volume. And that means that the liters would equal the moles divided by the molarity. So doing that, we got 0.225 moles of sodium hydroxide. Once again, I'm going to use the molarity of the sodium hydroxide as moles per liter, so I can see both units. And that means I'm really going to be dividing in this case by 1.420 moles per liter of sodium hydroxide. The moles of hydroxide will cancel, and that will get me 1.42. 0.158 liters of sodium hydroxide, which is, if you times that by 1,000, 158 milliliters of sodium hydroxide. So if you did this titration, you would need to add 100, that's a lot, 158 milliliters of sodium hydroxide to reach the equivalence point in this titration. And that's really step number 4. And again, here, the deviation is we don't use molar mass, but we do use the molarity sort of formula here at the end as well. So in this particular problem, we actually use molarity twice at step number 2 and step number 4 in the process. Any questions on any of those steps? You obviously could do it all in one calculation if you wanted to, or you could get the answer like we did in each step. This is a place where I would say 99%, now we'll go 95, 92% of people would just lay up M1V1 equals M2V2, and you would get the answer wrong because you have the wrong multiple relationship. So again, this is a very common place where people will use that equation incorrectly. So do not be that person that uses it incorrectly. Yes. Any questions on that there? So let's take a look at another titration problem here. So let's say it required go with 32.5 milliliters of 0.175 molar potassium hydroxide to reach the equivalence point of a titration of let's do 27 milliliters of nitric acid. What is the molarity of the nitric acid? All right, so give it a try, see what you come up with here. Yeah, so let's take a look at this one. Once again, this is another titration type problem, so definitely need an equation. So we're going to do our nitric acid plus our potassium hydroxide. Once again, acid-base reactions, really double displacement reactions. You could think of them as positive, negative. But again, we always know water is usually a product, and that does come from the acid H plus and the OH minus from the base. So that usually will give us our water that we will get. The salt part is, again, the other ions that will come together properly. In this case, +1 for potassium, -1 for nitrate. So we do get an equation like this. We always want to make sure that it is balanced. And in this particular case, it is balanced in this case. Yeah. So we're actually balanced. The next thing we want to do is sort of analyze, what type of problem we're dealing with. We do know that we have 32.5 milliliters of our 0.175. And again, I'm going to convert it into moles per liter, the molarity. We do know for the nitric acid, we have 27 milliliters, and we are looking for the molarity in this case. So really, again, here, the only thing that we could get to moles from is the KOH, which means it is not a limiting reagent problem. It is just a basic stoichiometry problem at this point. We're going to use that stoichiometry problem to get to really the missing piece that we need to solve for the molarity. We already have really the liters. We need the moles. So that is where the stoichiometry part is going to come into play. We're going to use it to figure out the moles of the nitric acid. So we'll get started with that part of the calculation. Once again, we do need to convert this guy into liters. So we'll divide by 1,000, and that will get you 0.0325 liters. So 0.0325 liters of KOH. Using our molarity as a conversion factor, we're going to multiply by it, 0.175 moles per liter. Liters cancel, gets us 0.0325 times 0.175, gets us 0.00569 moles of KOH. Once again, we don't want KOH in this case. We do want to get to nitric acid. So this is really where the stoichiometry comes into play. In this case, it is a 1-to-1 relationship between those two from the balanced equation. And that is what we're going to use here. 1 mole of KOH gives us 1 mole of our nitric acid. That gets us 0.00569 moles of our nitric acid. Now that we have the moles of our nitric acid, we also have the liters. If we convert this to liters by, again, dividing by 1,000, will give us 0.027 liters. We actually can calculate the molarity here. And that would obviously equal the molarity, which if we do that, about the rounded number, we will end up with 0.211, we'll call it. And I'll use big M for our nitric acid, R, again, as we talked about, 0.211 moles per liter of nitric acid. Again, it is the same 4 steps that we've seen many times up to this point. Balance the equation, convert to moles. mole to mole relationship and convert those moles into some other unit. Really the same 4 steps in this particular case. Once again, you could do it all in one calculation if you wanted to. You get a hint. Now, if you used, just so we're all very, very clear about this, if you used M1 V1 equals M2 V2 here, you will get the right answer. And if you did that on an exam or a quiz, you will not get the full credit. Yes. So I want to see equations. I want to see it worked out like this. You just got lucky that you chose that equation and it happened to be a 1-to-1 relationship. Again, will not work in all problems, and it doesn't work in the previous problem. You again would have just got lucky. So just so we're clear, no misunderstanding. If it is a solution stoichiometry titration type question like this, I expect to see equations, I expect to see some stoichiometry, and I expect to see some dimensional analysis happening there in your question. If you lay up M1 V1 equals M2 V2, you'll get minimal points just for the right answer. Any questions on that? Any questions on how to do titration type problems or solution stoichiometry type problems? Okay. All right, so to finish up this chapter here, we're going to talk about a few other types of concentration units that aren't necessarily used as much as molarity. And there are a few what are sometimes referred to as percent concentrations. The first one is percent by mass, and this is sometimes referred to as percent M/M, or mass to mass percent. And that is the mass of a solute divided by the mass of a solution times 100%. And in this case, it is the bottom one that's really important because we talked about it earlier. The solution is made up of 2 things, the solute and the solvent. You got to make sure that you have both of those things in this calculation. The reason I say you have to be careful with that particular calculation is in these mass to mass percent type problems, it is very common that they will give you the mass of the solute and the mass of the solvent separate from one another, which means in a lot of cases, people will just be dividing by the solvent and not really the mass of the solution. So you got to make sure that you get both of those things together. And that's really the one that you have to watch out the most for. There are a couple of other percent concentration units. There's percent volume to volume, like in alcohol. That is the volume of solute over the volume of solution times 100%. That's like milliliters over milliliters, essentially. That one, you don't usually have to worry too much about the bottom one because usually they'll just give you the volume of the salt of the solution. You don't have to necessarily worry too much about it. There's also percent mass to volume, which is the mass of the solute over the volume of solution times 100%. So these are 3 common sort of percent concentrations that are sometimes used for solutions. And this is also why when we talked about the dilution equation that there's C1V1 equals C2V2, you could use this type of concentration in that formula as well. Also, you can use percent concentration really as conversion factors. So for example, if I had a 4.5% by mass sodium chloride solution, you could actually turn it into a usable conversion factor. What that basically means, like normal, if I have a percentage, you could assume 100, kind of keeps all the numbers the same. That would mean that you have 4.50 grams of sodium chloride and 100 grams of solution. Or if you needed to, you could flip it around. 100 grams of solution is 4.50 grams of sodium chloride. So sometimes you might want to convert it out and use it more like a dimensional analysis conversion factor, and you could do that. And it works the same for all of the sort of percent units. If you have percent volume to volume sodium chloride, that would mean you have 4.5 milliliters of sodium chloride and 100 milliliters of solution. Or again, if you needed to flip it around, 100 milliliters of solution, you have 4.5 milliliters of sodium chloride. And lastly, if you had a 4.5% mass to volume sodium chloride, that would mean you have 4.50 grams of sodium chloride in 100 milliliters of solution. Or if you needed to, in 100 milliliters of solution, You got 4.50 grams of sodium chloride. So sometimes it's easier than plugging into sort of the formula and just kind of approach it as a dimensional analysis sort of calculation and kind of convert those things into usable sort of conversion factors. Any questions on that there? All right, so you have one next, give it a go, see what you come up with. This one, we are looking to calculate the percent mass to mass. And again, that is the mass of the solute, mass of the solution times 100%. In this case, we're taking 2.5 grams of calcium chloride and mixing it with 50 grams of water. The calcium chloride here is our solute. It is the smaller part of the solution. The water here is our solvent in this case. So that is why here we have the mass of our solute, which is 2.5 grams. This is our solvent. So this is the important part of the calculation. We need to make sure that we do get the mass of the solution together, which is both the solute and the solvent. And at that point, we have everything that we need. We can take the 2.5 grams divided by not 50, but 52.5 grams times 100%. And that will give us something like 4.76%. And you can leave it percent m/m as the units, and you can put calcium chloride in there if you like in this particular case. Any questions on that one there? So again, definitely with the percent mass to mass, that mass of the solution is really important to make sure that you are not just taking the solvent by itself. Any questions on that there? Let's try another one here. So concentrated hydrochloric acid solution contains 37.2% by mass. What is that? Okay, so you definitely could, since we're doing percent mass to mass, you definitely could use the formula and really plug and chug into there the mass of the solute and mass of the solution times 100%. We are looking for the mass of the solute here because remember, as we talked about earlier today, the name of the solution is the solute. So if it asks you what is the mass of HCl, then that is definitely the mass of the solute. And that's how we know the 35.5 grams is actually the mass of the solution in this particular case. Now you could just plug and chug into that equation, or if you wanted to, because you were giving the percent by mass here, or mass percent, you could turn that into a conversion factor and use it as a conversion factor. So I'm going to do that. So 37.2% means I have 37.2 grams of HCl and 100 grams of solution. Or if I needed to, I could flip that conversion factor around. 100 grams of solution would give me 37.2 grams of HCl. In this case, we have the grams of solution, which is 35.5 grams of solution. We're going to use a conversion factor there on the left, which is 37.2 grams of HCl and 100 grams of solution. Grams of HCl cancel out, leaves us 13.2 grams of HCl, I think. Let's see here, 35.5 times 37.2 divided by 100, 13.2 grams. That is really the same math you would do if you plugged all the numbers into here. It's basically the exact same math. So if you want to just plug it into the formula, you can, or if you want to do more of a dimensional analysis approach, you obviously could as well. They both come out basically the same. Any questions on that one there? Now, another unit of concentration that we definitely will come across a lot in towards the end of the year here, which I guess is coming up in a few weeks. So I guess that's good, right? So towards the end of the semester is molality, which is different than molarity. And sometimes they are confused with each other, but molality and molarity are different things. And if we look at what molality is the moles of solute per kilogram of solution. Molality is actually abbreviated with a lowercase m, and that's not mass in this case, it's actually molality. So molality is moles of solute over kilograms of solvent. Remember that molarity, which is capital M, is moles of solute over liters of solution. We will see molality a lot in, like I said, colligative properties that we'll talk about towards the end of the semester. The relationship between molarity and molality is usually it is like density that kind of ties those two together. It allows you to kind of go back and forth between those. The density is oftentimes sort of the thing that will allow that transition to occur. So let's take a look at a problem like this. Calculate the molality of a solution prepared by dissolving 61.7 grams of our C3H7OH in 175 milliliters of water. So again, here we're looking at molality, which is our moles of solute over kilograms of solvent. Our solute in this case is this guy. So we do have the grams, so we need to convert it into moles. So we're going to need the molar mass of our C3H7OH, as that's our solute. And that would be 3 times 1201 plus 7 times 1.008 plus a 16 and one more oxygen, hydrogen as well, 1.008. That gets us, we got here 3 times 12.01 plus 8 times 1.008 plus a 16. Looks like 6009 grams per mole. So we'll use the molar mass and the mass of our solute to convert it into moles. We're going to divide by the grams here to get to moles. The 61.7 divided by our answer is going to give us 1.027 moles. Now, in terms of the kilograms of solvent, we have 175 milliliters of our water, which is our solvent, but we need to get it to kilograms. And that is why the density is given to us. So if we use the density of water, density is mass divided by volume, which means the mass is volume times density. And if we do that, we would take 175 milliliters times the density of our solvent, which is water, 1 gram per milliliter, means that we have 175 grams of water. We do not need grams, though, here for molality. We need kilograms. So we got to do one more conversion here. There are 1,000 grams in a kilogram. So those guys will cancel. Gives us 0.175 kilograms of our solvent. We now have the moles. We now have the kilograms of our solvent. So our molality in this case would be our moles divided by our kilograms. And we will end up with 5.87. The units here do not cancel, so you can leave it as moles per kilogram. Or much like molarity, you could do 5.87 and little m, which again stands for molality in this case. Any questions on that there? So molality, like I said, we definitely will see a number of it towards the end of the chapter, end of the semester when we talk about colligative properties. And again, it is not molarity, and it has kilograms on the bottom rather than liters. The last sort of unit that's sort of like a concentration unit, or that's used sometimes in conjunction with concentrations, is a unit that we'll see in a couple places, including at the end with molality. But we also see it in the next chapter, which is gases, and that is mole fraction. So mole fractions is also used sometimes with sort of concentrations of solutions. And the mole fraction The mole fraction is basically like the percentage of each mole without the percentage part. So it's basically you do like a percentage calculation without dividing by the percentage. So basically the mole fraction, which is abbreviated with an X, you take the moles, for example, of A divided by the total moles that are present. So if you had a mixture of like A and B together, you would find out the total moles, and you take the moles of A divided by the total moles. Again, it's not times by 100 here, so it's not a percentage, but it's very similar basically to a percentage. So to see how that works, if we take this problem here, calculate the mole fraction of methyl alcohol in a solution where we mix 0.328 moles of methyl alcohol with 0.929 moles of ethyl alcohol. So basically here we have moles of our CH3OH, which is 0.328 moles. We have our moles of our ethanol basically, which is 0.929 moles. So we could get our total moles in this case by adding those guys together. And if we do that, we get 0.328 plus 0.929 gives us a total moles of 1.257 moles. So really at this point, it is much like a fraction. So we're interested in the mole fraction of methanol. So the mole fraction here of methanol would be the moles of methanol, 0.328 divided by the total moles. And once again here, we're not going to multiply by 100. So we'll end up with 1.257, maybe 257. 0.261 is our mole fraction. Basically, that is, it's 26% methanol in this mixture. If we wanted the mole fraction for ethanol, which was not the question here, we could do the same calculation. 0.929, which is the moles of ethanol divided by the total moles. And that will get us our mole fraction for our other guy, which is basically 74% as well. By the way, because these were the only two things here, I could have took 1 minus the mole fraction of methanol. That'd be like taking 100% minus it, and you would get the mole fraction there of ethanol. So mole fraction, we will see in the next chapter with gases. We will also see it towards the end there when we talk about colligative properties with molality as well. Any question on those type of things there? All right, that wraps up this chapter.